Other questions for anybody? Is there a way for you to know what you got right and wrong? Yeah, I posted the answer key just a little while ago. I edited it as much as I could. So it's been posted, Anna. So you can review it. I just put it underneath the exam in the exam module. You can ask me about a particular problem and I can scroll to it right now. This is the answer key. So trying to think of problems that people struggle with. I mean, the average on this exam was pretty, better than usual. It was like right around 70, or I can't remember exactly. But it wasn't too bad. Let me see if I even have it. I don't know. No, I don't have it here. Never mind. More questions? No more questions? I felt bad for not being here the other night. Let's see. So most people got that one. This one was one. Problem 10 was, since you're all just sitting here, problem 10 was one of those that people struggled with for some reason. If the reaction is dependent on ozone, that means that it's going to be dependent on this reaction here, so that you needed to take into account the reaction concentrations of both the ozone and the nitrate, the NO2, I mean. So that was one problem where a lot of people forgot and they left off the NO2 for some reason. So that was one thing that people struggled with that I don't know if it was any of you or not. I don't remember. This one for some people was a struggle as well. Needed to recognize that if you had the rate of disappearance at 4.0 of A, right? So if A was, right, A had a rate of disappearance, it's equal to 4.0 times 10 to the minus 2. Then we had, when you had B, right, was equal to 2.0 times 10 to the minus 2. That's a 2, right? And then C was 6.0 times 10 to the minus 2. And then you had to just figure out reaction stoichiometry and just recognize that this, if you had, an A to B to C ratio, that you need to figure out that you had, well, first of all, that since A was disappearing and B and C were appearing, that you needed to recognize. Did I put the wrong answer down here? I actually might have graded this one wrong. It's a good thing you guys ask me questions. I find the answers that are wrong. This should have been C, but I don't know if I put C in or not. I'm going to have to look, see if I actually graded this one incorrectly. The answer should have been, I might have to do a regrade on this. It should have been, you have a ratio, right, of a 1 to 2 to 3 ratio. So there should be a 1 to 2 to 3 ratio. And since A is disappearing, it goes on the left by itself, and B and C go on the right by itself. Did I grade anybody's wrong? Did everybody get that one right? So I might have just entered it wrong in my answer key. I'm gonna look really quick. Yes, correct. Did I grade it incorrectly? Did you get it right? Did I mark you wrong? Let's see, what did I put for the answer there? Is there a way to unlock viewing of our submitted exams so we know what we put for the multiple choice? It doesn't tell you. I don't know what your side looks like. So, and there's nothing on my end that allows me to do that. Really? It doesn't allow you to see which one you got wrong? I will have to figure that out. That I am not aware of. So this is question 11. Let's see. Let's see what I put for answer here. No, okay, I did it correctly. I graded it correctly. Don't mind me. So I didn't do anything wrong there. I just put the wrong answer in my answer key here. So this is not correct. But I graded it correctly. All right, so that's not correct. This was correct. I will need to look into. It says that they are hidden. Let me see what the settings are. Huh. Does it allow you to look at them now? Can you refresh your browser? Or do I have to actually click on names? Huh. This is really strange. Still says the correct answers are hidden. We have somebody in the class who hasn't dropped it. And unfortunately, how do I change that? That's my problem, is that that person hasn't taken it. Let me see. Let me see what happens if I select everybody. 4, 5, 6. Let me go to Canvas guides. Sorry, I don't know why it's not showing. I didn't know that you couldn't see the answers. Of course, they don't show us that. There's no help key for that. I'm trying to change it, but I don't know what I'm doing. Let me see if I can edit this. So I can actually do this. Right, so if you refresh now, can you see? I just tried changing a setting. It's really strange. Okay, good. All right. Yeah, there's a little checkbox that I had to click. It was buried under another checkbox. That wasn't clear. Well, now I know how to do that. I learned something today. I can retire for the end of the evening. Anyone else have questions? We have any new people? Nope. I lost Sophia. Just Anna and Catherine. I can look at core number 17. Yes. Oops, too far. Number 17. So the question was at 448 degrees Celsius, the equilibrium constant Kc for the reaction of hydrogen, right, hydrogen plus iodine going to 2HI as a gas is 50.5. Predict in which direction the reaction proceeds to reach the equilibrium if we start with 2.0 times 10 to the minus 2 moles of HI, 1.0 times 10 to the minus 2 moles of H2, and 3.0 times 10 to the minus 2 moles of I2 in a 2-liter container. And it says, first determine the starting concentration of each species. This is going to be, then you're going to substitute the starting concentrations into the equilibrium constant expression to calculate the reaction quotient Q, right? So we have our Kc of our reaction, right? We calculate our Kc of the reaction where we have products over reactants first, and then we just plug in Q first, right? And we need to plug in our initial concentrations. So the first thing you need to do is you need to convert all the moles to molarities. So since you need to divide by the number of liters of the vessel. So this gives you the concentrations of each of the initial substances. And then you just simply plug them in here, right? You plug them all into your Kc or your Qc reaction. You get 1.3. And then you compare this 1.3 to the 50.5. Right? And because the 1.3, the QC, is less than the 50.5, you're going to have, if you think about what this means in regards to the equation, right? If we have a number that's smaller, right, that means the numerator is going to be smaller, or the denominator is larger, whichever way you want to look at it. So the numerator is smaller, it means you have you have less product there. So the concentration of the HI, the product, has to increase, and the concentration of H2 and I2 have to decrease. And because of that, you're going to need the reaction to proceed to the right-hand side. So because you have less HI on the right here, you're going to need the reaction to proceed to the right-hand side. And that way you can balance the reaction out and end up closer to a 50.5 ratio. Does that make sense? Or do you want me to explain something different? Feel free to unmute yourself if you want to ask. Overcomplicated it a lot, probably, yeah. That happens too often. I also did put comments on people's worksheets too, so feel free to look at your worksheets because I added comments there when I could. Other questions? Go over 3 and 4. Yep. No new people yet. Nope. All right. 3 and 4. Oops. All right. So 3 and 4 were just two parts of the same exact question. I originally had it was going to be a part A, part B. So when we're talking about, we can just do one of them. When we're talking about the rate of appearance of NO2, right? The rate of appearance of NO2 in the following reaction at a particular instant is 2.1, right? So we have that 2.1 is the rate of appearance of N2O2. If we want to talk about the rate of appearance of N2O2 in terms of N2O5, we need to have a ratio, right? So we know that we have 4 moles of NO2 is equal to 2 moles of N2O5. Right, this is just equality. This is just coming from our mole-to-mole ratio. And what we're able to do with that is, right, we can turn this into conversion factors. So we just turn that into our conversion factor here, where if we want to convert our molarity, right, the molarity that's here in NO2 over, all we have to do is simply multiply by the conversion factor so that the moles of NO2 are going to cancel out, right? Because if we look at this, right, this is 2.1 times 10 to the minus 7 moles per liter, right, per 1 liter per 1 second, times, and this is mole. Let me just actually put the data in there. Okay, this is actually moles of NO2. Right? And we're going to simply multiply that by 1 mole N2O5 divided by the 2, I'm sorry, not 1 mole, 2 moles of N2O5 divided by the 4 moles of NO2, right? So then the moles of NO2 are going to cancel, and they're simply multiply by 2 divided by 4, so multiply by a half, whatever. And you can see how the mole of N2O5 is then going to move over into the numerator of the equation, right? So this is going to move over into the numerator of the equation, and you end up with, you know, the 1 point would be 1.05, right? Which you're going to have to round up to 1.1. 1.95 times 10 to the minus 7 mole N2O5 per liter per second, for 1 second. Right, so then you can just recombine this part into molarity, and you end up with, after rounding, 1.1 times 10 to the minus 7. That makes sense? Then for the, obviously for the O2 one, it's your ratio is just 4 to 1. Right, so you're getting a 4 to 1 ratio. So you divide it by 4 to get the answer here. Yes, equations on the sheets. I always hesitate, and it's one of the reasons why I try to, sometimes I think it might even be worse to give you equations on sheets, because people think you have to use them all. And then they overthink. It's a lot simpler than you thought, right? Other questions? Equilibrium of number 24. Oops, I go too far. Here we go. All right, so this doesn't show you that in there, but all right. So for this one, when you're working through the concentration, you first need to recognize, right, that you need to use that percent ionization in this problem to get your equilibrium concentration of H plus, right? And all that percent ionization is, right, when we think about, right, our percent ionization is just equal to our, what am I trying to say? Is just equal to the, what's the word I'm trying to, I can't even think of the word right now. Mind went blank. Is equal to the concentration of our HA, right, times, and my mind just completely left me as to what I wanted to say. Let me see. Okay, give me 1 second. Right. So if we're looking at our percent ionization, my mind is gone. Huh. I didn't give you that, did I? All right. So when we're thinking of percent ionization is just, the quantity, and let me just dig up this number. My mind is gone. I'm ready to go to sleep. I wake up too early now. That's in chapter 16, right? been a crazy day today. Percent 682. All right, there we go. There we go. That's what I want to do. All right, concentration of our HA, ionized HA. That's what I wanted to do. That's why I was like sleeping over here. Percent is the concentration of HA that's been ionized. Right, it's ionized. Divided by our original concentration of HA. There we go. Times 100%. And when we figure out what our percent ionized, so if our percent that's ionized, right, so is equal to our H plus concentration, right? So if we have our, right, so this is going to be essentially our H plus concentration is going to be the percent that is ionized. And this is the H plus at equilibrium. And we know that in this particular example, that's 11%, right? So 11% of this has been ionized. So the number that we're going to plug into this equation is just, 0.11 times our HA initial. So this is, just 11% of our initial is going to be what this is equal to here. Does that make sense? So we know that the H plus is just, that's what they came up with the equation here, right? It's 0.1 times the initial. And we know that our initial concentration here is the, when we're figuring it out, it's a 0.100 molar solution. Our initial concentration of acid and of the conjugate base are going to be 0. But we know that this 0.0110 molar solution, right, this equilibrium concentration that's here is that 11%, right? That's where the 11% comes in. This is just 11% of the initial concentration. That's how much gets ionized. So then we had to add 0.0, we just got too many spaces in here. I'm going to put the change down below, right? So, they left the change out here, right? The change is equal to plus 0.0110 plus 0.110. And this one's going to be minus 0.0110. So when you subtract these two, you end up with the 0.089. So that ends up with the equilibrium concentration that you can then plug in to the Ka equation. This was exactly like sample problem. Actually, I think it was like a merge between two different sample problems. Where are they? I can't find them. It was just like two different sample problems, the last two that we worked on before the exam. The percent ionization problems. It was 1610. It was a merge of 1610 and 1611. So whichever one 1610 and 1611 are here, if you can find the sample problems. Or if you look at problem 1610 and 1611, it's exactly where the, it's a merging of those two problems. Did that answer your question? I hope. All right. Overcomplicating it is a very common problem on chemistry exams. If you in my class, just realize I'm not ever trying to trick you. My goal is not tricking you. My goal is to try to test comprehension. So sometimes I'm going to ask, easy questions to make sure you understand it. That's why I don't like multiple choice exams, which is why I didn't have many multiple choices on this exam, which is why it took me, 9 hours to grade. So it's because, multiple choice is basically multiple trick. My goal is to trick you into the wrong answer, and I don't like doing that. But anyway, okay. Anna has another question. Could you explain the wording of question 10? Why does it say the rate depends on the ozone? So it says if the reaction is dependent on the ozone concentration, what is the rate law of the experiment? So it's just asking you, so if you have your overall equation and then you have the two steps. And if your overall rate of your reaction has a dependence on ozone, then it has to be in this reaction here. So you have to basically then look at the entire reaction in order to determine your rate law. So it's not just ozone because you have to analyze the entire reaction. You know that there's an ozone component to your reaction, which is what is shown there, right? There's ozone. But you actually need to take into account that it also depends on the NO2 concentration as well. This one was worded really similarly to another problem that we did. I can't remember which one. This was rates. This one was really similar to problem sample exercise in the textbook 14.14. So it's really similar to 14.14 if you want to look at that for more detail. It's actually, as I'm looking at it, it's actually the practice exercise from 14.14. So if you did the practice exercises, then you would have gotten the answer. Elizabeth here. Hi, Elizabeth. 19. All right. So 19, this is for the reaction of 4 ammonia plus 5 oxygen goes to 4NO plus 6H2O with a delta H of minus 904 kilojoules. Which of the following changes will shift the equilibrium to the right toward the formation of more products? All right. So if we walk through them all, the answer here was C, increasing the volume of the reaction. If we look at A first, add more water vapor. Well, water vapor is on the left-hand side of the reaction, right? So if we look at that from that perspective, we place a stressor on the right-hand side, place a stressor on the right-hand side, the equilibrium will shift to the left. All right, does that make sense first? And then B, increasing the temperature, right? So increasing the temperature, so we have a reaction here. It has a delta H of minus 904 kilojoules. So that means that we have, our delta H here, right, is equal to minus 904. Right, so we have an exothermic reaction. So if you add heat to the reaction, then what you're doing is you're giving it enough energy so that it can go back up and over and head towards the left. Right, because the problem in this reaction, if you had it the other way around, if you had an endothermic reaction, right, an endothermic reaction that would just give you enough heat would basically allow you to go over to products. whereas in an exothermic reaction, heat drives the reaction in the reverse direction for equilibrium. I'll come to C last. We'll do D, removing the oxygen, right? So oxygen, because it's on the left-hand side, since you're taking O2 out, you want to rebalance the equation, so everything's going to shift to the left. E, adding 1 atmosphere of neon to the reaction vessel. Well, since neon doesn't appear anywhere in the equation, it has no effect whatsoever. And then the last one is increasing the volume of the reaction. So this is the one where we have reaction vessel, right? And if we have 4 NH3 gas molecules in here at equilibrium, we have 5 O2, we have 4 NO, and we have 6 H2O. Right. So if we make the reaction vessel double in size, then we basically have more space, and with that more space, we are able to accommodate the side of the reaction where we have 10 here, right? This gives us 10 products versus the 9 reactant gas molecules. So in the gas phase, when you have more space, you're going to favor expanding out, and the way to favor the expansion is to have the equilibrium shift towards the more number of gas molecules. So that's why it, C is the answer. Increasing the volume of the reaction is the answer. Make sense? Questions? Other questions? Any other new arrivals? We have a couple. We have Annie's here. Hi, Annie. Annie's lurking. What was the highest score? I don't remember. Let's see. Let me share the grades with everyone. No, just kidding. I will tell you the highest score was a 93.1. There, 93.1. And the average was right around a 70 or 72 or something like that, I think. It was 72, which isn't, outstanding, but it's not 50s and 60s, so it wasn't horrendous either. So Elizabeth, so it's expanding, and that makes it easier to form product. Yes, so it's because you're expanding, your equilibrium allows you to form more product from a. Let me try to think of how to describe this differently. It's I don't know. The description was on, where was it? They talk about shifting equilibrium. I don't remember. It's on the Chatelier's principle, and so on the Chatelier's principle, pages 647, 648 in the textbook, talks about volume changes, and pressure. Yeah, so if you would take a look in 647, 648, talks about the effects of volume on this volume and pressure. Think about it this way. Let's just say instead I started with an equilibrium here where, you know, a larger flask, and I shrank the flask, right? So if I shrink the flask down, the gas molecules are going to start to compress, right? As I'm compressing, like, you know, let's say as I shrink it down, keep shrinking the flask down, I'm compressing the gas molecules so they're getting closer and closer together because I'm shrinking the volume. And in order to accommodate the shrinking volume, the equilibrium is going to shift from, you know, the side where you have 10 gas molecules to the side that you have 9 gas molecules. So conversely, as I expand the volume, the equilibrium is going to shift in the opposite direction. To start to fill the flask, it's going to shift towards the side that has more gas molecules, and, you know, away from the side that has less gas molecules. All right. Other questions? Yes. Why is my mouse working? Oh, there's this one right here. All right. So for problem 20, I gave credit to both A and C. And, oh, okay. I give it credit to both A and C for this. So number 1 only, or number 1 and number 3. So when we're looking at the dihydrogen phosphate, the H2PO4, right? So we want H2PO4. It's amphiprotic, and it's asking where is it serving as a base. So whenever, obviously, you know, if you think about H2PO4, if it acts as a base, it's going to be, you know, reacting with a proton of some sort to eventually form the H3PO4, right? That's how it's acting as a base. So it has to react with some type of proton in order to act as a base. So in the first case, the H2PO4, right, is doing exactly that. It's reacting, instead of with H3O, it's with H plus, it's reacting with H3O plus, right? So then it just basically releases the water out in the end. And because it's acting as the acid is here, it's acting as a base here to produce the conjugate acid and the conjugate base. In the second example, the H2PO4 is here on the right-hand side of the equation. And you can see that in order for it to then go to the left-hand side, there should be double-headed arrows here. For it to move to the left-hand side, it needs to act as an acid, right? Heading towards the left, it's acting as an acid because it's giving up one of its protons to the water. So the water is acting as the base here. The H2PO4 is acting as an acid, and then it gives it off. In the last example, it's on the product side here where it's reacting with itself, right? So it's H2PO4. My computer literally just froze. There we go. Everybody's frozen. I think I need to try to exit out of here because I just froze completely. I got nothing. Teams just took over my computer. It said, you are done. Wow, I got nothing. No response at all. I think I might need to reboot and log back in. So I got nothing. No response whatsoever. Alrighty, I'm back. Can everyone hear me now? Can anyone hear me? All right, good. Well, I see nothing that I was writing actually passed through. So it must have frozen. I must have been babbling for a while before I was real. My phone computer just went completely dead. So I don't know where I left off. What I was discussing was, H2PO4 minus, in order to act as a base, has to pick up some type of proton. And when it does, results in it producing H3PO4. Right. So when I started working through the examples here, you can see in the first case, it's reacting with the H3O plus and producing the H3PO4 minus. So right, it's doing exactly like I said here. In order to act as a base, it's going to be, right, in order to act as a base, it has to react with an acid, and then it produces its conjugate acid here on the right-hand side. And in this first example, it's reacting with H3O plus, right? And it's producing the conjugate base of water as a byproduct. Right? So it produces H3PO4. In the second example, what I was saying was it's reacting with H2O2. And when it reacts with H2O2, it's producing the HPO4 2 minus. Right? So in this case, it's going in the opposite direction. It's acting as an acid and reacting with water, and water is acting as a base. So it's producing the HPO4 2 minus and the conjugate acid of water. So in this case, it's acting as a base, so that doesn't count. And then in the last case, we have it reacting with itself, right? So you have H2PO4 minus reacting with another H2PO4 minus in equilibrium, right, producing HPO4 2 minus plus the H3PO4. Right, so you can see one of these, you can pick either one is acting as an acid, the other one's acting as a base. And in doing so, it's basically picking up a proton. Let's just say this is the case where it's acting as a base. Here's the one where it acts as the acid, right? So then this becomes the conjugate base, right? This is the link between these two. The conjugate base there, and the conjugate acid is out here. So that's how it ends up acting as base. Now, technically, I ended up giving points for both A and C here, for both 1 and 3. But technically speaking, the correct answer for this is only 1. Why is 1 only technically the correct answer for this? Either one of you want to give me a guess? Why is 1? Oh. Why is 1 acting as the only case where it's actually acting as a base? Or maybe I'll ask the question a different way. If you were labeling this H2PO4 and the reaction number 3, would you label it as the acid, the base, conjugate acid, or the conjugate base? Anyone? What do you think? A, B, CA, or CB? No one wants to say anything? Can you still hear me? Or am I frozen again? Are you still there? Could I repeat the question? Yes. So if we're looking at equation number 3, H3PO4, right? And this is H3PO4, HPO4 2 minus going into form 2 H2PO4 minuses. What would we, if we were to label what H2PO4 is in this equation, we would label it as the acid, the base, the conjugate acid, or the conjugate base. Conjugate base, right? And also a conjugate acid, because there are 2 of them, and one of them is acting as a acid, one's acting as a base. So the technical answer for this question should have been that 1 was only, the answer is technically it only acts as a base in equation 1, right? It acts as a base here. It's acting as a conjugate acid and a conjugate base in example number 3. So, but I gave credit to both. Any other questions? Did that answer your question, Catherine? So I think you asked this question originally. Any other questions? Going once. Going twice. That was good. All right. Thanks, guys, ladies. Have a good night. I see you on Friday.